In this video, I'm going to introduce to you what a fully connected neural network is and how to convert it to matrices so that you can compute it on the GPU. In order to convert this neural network into matrices, we need to learn what a fully connected neural network is. So a fully connected neural network is made up of neurons, where the neurons belong to three different types of layers: an input layer, a hidden layer, or an output layer. In a fully connected neural network, each neuron in a layer connects to each neuron in the layer in front of it until it reaches the output layer. And each connection that's between two neurons has a weight associated with it. So the neuron that's sending information will have its value amplified, suppressed, or inverted by multiplying the value by the weight. And this will equal some value that we can call z, and this value is going to go to the next neuron. At the same time, other connection values will be entering the neuron. And the way that this neuron handles the incoming connections is by summing up the connection values, then inserting that value into a function that you can choose. And the output of this neuron's value could be the final result if the neuron is in an output layer. Otherwise, it's sent to neurons in the next layer ahead of it. And some example functions that you can use could be the sigmoid, the rectifier, or the hyperbolic tangent. So now that we have an understanding of how information is passed through this type of network, we can begin the process of converting it to matrices. I'll start with this neural network and take the first two layers of it and name the input layer neurons A, B, and C. And then I can assign identities to the connections. With this, I can write expressions for the neurons in the next layer. So the first neuron in this layer is going to equal A times weight 1 plus B times weight 5 plus C times weight 9. The second neuron will equal A times weight 2 plus B times weight 6 plus C times weight 10. The third neuron will equal A times weight 3 plus B times weight 7 plus C times weight 11. And the fourth neuron will equal A times weight 4 plus B times weight 8 plus C times weight 12. And each of these expressions that represent the neuron will have to be passed through a function eventually. But for now, let's use them to represent the result matrix from a multiplication operation, which as is would be a 4x1 matrix. Then we can use this matrix to define the left and right matrices needed. Because this entry's value, which is in the first row and first column of the result matrix, is defined by summing the products of the first row in the left matrix by the first column in the right matrix. And this left and right matrix is arbitrary for now. So we can begin to sum the products starting with this part in the result matrix. We can insert A into the left matrix, and we can insert weight 1 into the right matrix. And for the next part, we can insert B into the left matrix and weight 5 into the right matrix. And then do the same thing for the next part. So we still have 3 entries to evaluate from the result matrix. And evaluating the second entry shows us that the second row of the left matrix and the first column of the right matrix make up these values. Which is actually a problem, because if we were to go through with it, a copy of the A, B, and C values would be created in this row, and the new weights would write over the existing weights. So in order to fix this problem, we need to make the result matrix have 1 row and 4 columns, instead of 4 rows and 1 column. Doing so will allow us to have the right amount of rows and columns for the left and right matrices. Analyzing the first row and the first column in the new result matrix is going to give the same entry values in the left and right matrices as shown here. But now when we go over the first row and second column of the result matrix, we get to reuse the values of the neurons that make up the left matrix. And the weights in the right matrix doesn't get written over, and we can insert the correct values. So continuing through this result matrix, we can enter the values into the left and right matrix. Now that there are no more entries in the result matrix to evaluate, the left matrix will have 1 row and 3 columns, and the right matrix will have 3 rows and 4 columns. And we can verify that this matrix multiplication operation will work by checking how many rows and columns each matrix should have. So the left matrix needs to be an M by R, the right matrix needs to be an R by N, and the result matrix needs to be an M by N. It looks like the M's match, the R's match, and looks like the N's match. So to review what we did, we took 2 connected layers from some random network and made matrix representations of the computational process. And the values in this result matrix is not the final neuron values. This is only the summation of all the incoming connections per neuron. We still have to pass these values through the neuron's function. So for any matrix that represents the summation of connection values from other neurons, we need to pass the values in this matrix through a function. And these values in the updated matrix will then be the correct outputs for the neurons in this layer. So to wrap this all up, we can represent any two connected layers as a matrix multiplication operation, where the left matrix has one row and a column amount that equals the number of neurons in the first layer of the network, and the right matrix represents the weight values of the connections with a row amount that equals to the number of neurons in the first layer of the network and a column amount that equals to the number of neurons in the second layer of the network. And the result matrix will have one row and a column amount that's equal to the number of neurons in the right layer of the network. Thanks for watching. If you like this video, you can subscribe to my channel to support it. Also, if you have any comments about the video, you can leave them below.